Okay, so today we have lesson 7, calculation of probabilities of compound events. This is kind of like a continuation of what we did last lesson. If we remember, a compound event means it has more than one outcome. That is what that means. And then it says a previous lesson introduced tree diagrams. We should remember that. We're going to come back today to our example about the game with the four-sided die, the card game or the board game. And then it said that this is primarily, when we did it, it was focused on cases with 2 stages, but now we're going to do it with more than 2 stages is what we're doing today. So we're just taking it a little bit further, same stuff though. So before we start the lesson, I want to clear something up. This is something that was confusing me, and then I found this helpful visual that I thought we would share. Why do we multiply the probabilities? You hopefully remember that when we are doing the probabilities of one or more independent events, so compound events, we multiply our probabilities. So let's look at this visual example right here. It says event A happens 1/2 of the time, and then event B happens 1/3 of the time. So these would be events that happen in order. So event A would happen first, and event B would happen second. So if we are looking at this first one, it's out of 60 chances. So each one of these kind of holes represents all of the outcomes, right? So the first event is event A, and it happens 1/2 of the time. So if we look here, we have 1/2 of these A's, or 1/2 of the chances turned into A's, right? So this is 30 out of 60 is going to be an A, which is a 1/2, right? And now event B happens second, we remember, and it happens 1/3 of the time. So that means if we look at our next picture, we have to mark off 1/3 of our A's, because event A happens 1/2 of the time, and then event B happens 1/3 of that 1/2. So we know that 1/3 of 30 is 10, because we know that 30 divided by 3 is 10, right? So these X's right here represent this 1/3 of this original 1/2 of the A's, right? So this 1/3 of 1/2, if we count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we know it's 10. 10 over 60 can be simplified to 1 over 6. And then if we do our 1/2 times 1/3, which we know we have to do in the first place if we're just following our rules, 1 times 1 is 1, over 2 times 3 is 6. So we get the same thing. This is why we multiply. And if you're wondering over here about these B's over here, that's because event B happens 1/3 of the time. It could either happen in either of these halves, right? It could happen when A happens first, or it can happen if A doesn't happen first and it just happens by itself. But right now we are only talking about when A happens first, so we're only looking on this side. But I just saw this visual on why we multiply for probability. It really helped me out to think about it, so I wanted to share it. So again, we multiply our independent events for probability. As you can see here, we have to find out what 1/3 of 1/2 is, which is the same thing as 1/2 times 1/3. Hopefully this will help us moving on. So moving on to the actual lesson. Oh shoot, sorry, that was me trying to plan this out. This is our first example. This is throwback to our last lesson, the same example. We're just going to do some more problems and apply some new stuff to it. So it says, recall a previous example where a family decides to play a game each night. They all agree to use the tetrahedral die. Remember, this is 4-sided. Each night to randomly determine if the game will either be a board game or a card game. The tree diagram matching the possible outcomes over 2 consecutive nights was as followed. This is what we created last lesson, and a quick review of a tree diagram. So here are our 2 days. We have our Monday and our Tuesday. And so on Monday, we could either do a board game or a card game. And then on Tuesday, we have the same thing. On Tuesday, we could also either do a board game or a card game. So we go like this, and we bring our board game or card game up. And then again, we could also do a board game or a card game, and that gives us our outcome. So we could either do board game. So Monday, we have a board game. when we're looking at these outcomes right here, we can kind of split it down the middle and look at this like Monday or Tuesday, right? So Monday we had a board game, Tuesday we had a board game, Monday board game, Tuesday card game, or Monday card, Tuesday board, Monday card, Tuesday card. Just a quick review of how we got that last lesson. So now we're going to expand on it and bring in Wednesday. How would the diagram change if you were interested in mapping the possible overall outcomes over 3 consecutive nights? To accommodate this additional third stage, you would take steps similar to what you did before. You would attach all probabilities for the third stage to each branch of the previous stage. So, kind of giving us a lot of information. Let's go ahead and look at our problems to see what they're asking me to do. If BBB represents 3 straight nights of board games, so that means Monday we have a board game, Tuesday we have a board game, Wednesday we have a board game, right? BBB, Monday, Tuesday, Wednesday, we're following straight along with the tree. What does CBB represent? So, if we're following straight along with this, the tree right here, C comes first and Monday comes first, so that means that Monday would be a card game. The next one is B, that means Tuesday would be a board game. And then the next one is B again, so that would be, that would mean Wednesday we play a board game. So the thing to take away from this one is that the order in which it happens is important. So it doesn't just mean 1 card game and 2 board games. It means on Monday we play a card game, and then on Tuesday we play a board game, and then on Wednesday we play a board game. So that's important to remember. It's not just 1 card game, 2 board games. You have to tie the day into it. So let's look at our next one. It says list all outcomes where exactly 2 board games were played over 3 days. How many outcomes were there? So in this one, I just said that the days matter, but the question is just saying exactly 2 board games, okay? So we have to look back to our tree diagram and see which ones have 2 Bs. So I see, it says exactly 2, right? So if it says exactly 2, if I look at my first one, BBB, that's 3 Bs, we can't count it because it doesn't have exactly 2. So we have BBC, that has 2, BCB, 2 Bs, 2 Bs here, and I think that's it. Yes, those are the only ones with exactly 2 Bs. So the ones that we have are, we have the probability of BBC, we have the probability of BCB, and we have the probability of CBB. So how many outcomes were there? We have 1 here, 1 here, 1 here, 3 outcomes. So let's look at question number 3. There are 8 possible outcomes representing the 3 nights. That's just what they're saying here. 1, 2, 3, 4, 5, 6, 7, 8. They're just talking about this column right here where the outcomes are. So, are the 8 outcomes representing the 3 nights equally likely? Why or why not? So, are these equally likely? To answer this question, we have to remember some information from our last lesson. We should remember that the chance of a board game and a card game are not equally likely. The chance of getting a board game is 0.75, and the chance of getting a card game is 0.25. So if these 2 right here, the only 2 outcomes, the chances are different, are the 8 possible outcomes going to be equally likely? The answer is no. They cannot be equally likely because we have a different chance of getting each of the 2 choices. So right here, if we have a B, and a B, 0.75 times 0.75 times 0.75, that's going to be different than 0.75 times right here would be 0.25, and right here would be 0.25. So they're not going to be equally likely. And why not is because they have a different likelihood of occurring in the first place. I'm not going to write that down because it's too long, so sorry. Moving on. We're expanding on this again. It says, what is some new information? A lot of this is old information. Example 1, each night's outcome is the result of a chance experiment. There's a probability associated with each night's outcome. By multiplying the probabilities, you can obtain the probability for each branch of the tree. This is what I talked about with the visual. We're multiplying the probabilities. So it says, for this family, a card game will be played if the die lands on a value showing 1, and a board game if it is 2, 3, or 4. That makes the probability of B 0.75, which we knew, and it makes the probability of C 0.25, which we knew. Let's use the tree to examine the probabilities of the outcomes for the 3 days. So the first thing that I'm going to do, that way I don't get confused later, is I'm going to put my probabilities under each letter just to help me follow along. So I know every B is going to be 0.75 and every C is going to be 0.25. So let me just do that real quick. 0.25, 0.75. Maybe color coding would have helped here. I'm going to do that for next time. Okay, so calculate the approximate probabilities for the remaining ones. So we're just going to go along our tree. I am going to use a different color now. So our first one, BBB, that's this branch of the tree right here. So this means you have to do 0.75 times 0.75 times 0.75. So for this one, when we go ahead and put that in our calculator, I thought that I could pull it up on the screen, but I can't figure it out. So hopefully you have a calculator on your phone or wherever you are. You could do 0.75 times 0.75 times 0.75, which should get you 0.421875. We're going to round to 3 decimal places here, so that will be 0.422. Okay, so now for our next one, we'll do another color. We have BBC, so we follow the train. BBC, so that means we have to do 0.75 times 0.75 times 0.25. Go ahead and do that on your calculator. 0.75 times 0.75 times 0.25 is going to equal 0.140625. Again, 3 decimal places, so 0.141. And now I'm going to pause this recording and then come back with them all filled in. Go ahead and do this on your own. Take a minute to do that. Okay, so hopefully you have gotten all your probabilities. And you should notice a little pattern here. So you should notice some repeating ones, some that are the same, and some that are different. What we have here is our one right here in blue is unique because it's the only one with 3 B's. So this is a unique probability, BBB. Also down here, CCC, the only one with 3 C's. So these two are separate. And then we have another group, that's our 0.047s, which these are our ones with 2C, 1B. Oh shoot, 2C and 1B. And then our other group is our 0.141s, which is with 2 B's and 1 C. So if you figured out those patterns, you didn't have to actually multiply through everyone. You can just see, for example, BBC right here and BCB. If you did the first one, you would notice you did 0.75 times 0.75 times 0.25, and then as you were doing the next one, you could say, oh, I know that when you multiply, it doesn't matter the order, so these will be the same. So what you should see is these different groups. You should see that pattern. So that was our answer to number 4. Let's look at number 5. What is the probability that there will be exactly 2 nights of board games over the 3 nights? Okay, so that means exactly 2 nights. Let me get a color that we haven't used yet. Exactly 2 nights. So that means I need 2 C's. I'm sorry, it means I need 2 B's because this is board games. So that means I need 2 B's. So how many options are there where there's 2 B's? We have this one, BBC, BCB, and CBB. These are all our 141s, right? So this is our probability of BBC, our probability of BCB, and our probability of CBB. So now the question is, how am I going to find this? What is the probability that there are exactly 2 nights of board games over the 3 nights? We have been multiplying probability previously, but when we were multiplying, that was kind of like when our events are happening back to back, right? So Monday, then Tuesday, then Wednesday. We're multiplying those together. This is not asking for back-to-back events, right? This is just saying that of all of these 8, what is the probability that these 3 out of these 8 are going to happen? So instead of multiplying, we're actually going to add these. So what we can do is we can take, we know these are our 141s, so we're going to do 0.141 plus 0.141 plus 0.141, or if you're intuitive, 0.141 times 3 is the same thing. So this is us adding the probability of BBC, probability of BCB, and the probability of CBB. These are all the ones with 2 board games. So 0.141 times 3, or 0.141, 0.144 plus 0.141 plus 0.141 is going to equal to 3 decimal places 0.423. So when we move that little decimal, that's a nice 42% chance. So last question on this page. What is the probability that the family will play at least 1 night of card games? So this is at least 1 night. Let's do a different color for this one. Sorry, it's getting a little bit messy. At least 1 night of card games. So if you remember our at least questions, that should ring a bell that we're probably going to be doing our 1 minus the probability of something. Here we're doing the 1 minus the probability of no card or no board games, right? Or no. 1 minus the probability of no card games, sorry. The reason that we do 1 minus the probability of no cards, let me rewrite this so that it's neater, is because it's saying at least 1 night of card games. So this 1 is representing 100%. So when we're talking about no card games, which one is the only one with no card games? The only one with no C is our BBB up here. So we're doing 1 minus the probability of BBB, which is 1 minus 0.422. The reason that we're choosing this one is because there is no card games here. So if we're going to play a card game 100% of the time, this is that 100% of the time, except in this one time, you can do 100% minus this one time. So when you do 1 minus 0.422, you're going to get 0.578. However, if sometimes you forget about this or it's hard to think about, another way you could do this, it's a little bit longer, is that you're going to say at least 1 card game. You could realize that this one is the only one with no card game, so you could just add all of these together. All of the ones with card games you could add together to get the same thing. It just will take a little bit longer. Instead of saying 100% of the times, except this one time, 1 minus that one time. So whichever way is easier for you to remember, both work. Okay, these are our last examples here. It says, a neighboring family just welcomed their 3rd child. It turns out that all 3 of the children in this family are girls and that they are not twins or triplets. Suppose that for each birth, the probability of a boy birth is 0.5 and the probability of a girl birth is also 0.5. So they're saying that both probabilities are 0.5, meaning that they are equally likely. What are the chances of having 3 girls in a family's first 3 births? So let's look at the way they broke these questions down. The first part, number 7, I'm going to bring out the black pen. Draw a tree diagram showing the 8 possible birth outcomes for a family with 3 children. We're not going to do any births at the same time, no twins or triplets. So use B for boy, G for girl, and consider the first birth to be the first stage. So the way we're doing our tree diagram is up top where we have our titles. That's the order that they're coming in. So in the last example, if we look back, we had Monday, Tuesday, Wednesday. The order here now is our first child, our second child, and our third child. And then we have our outcomes over here. So when we're making this chart, we have to think, if we're talking about our first child, our second child, our third child, what are the options for our first child? The option for our first child is we could have a girl or a boy. So we put a G here and a B here, because you can either have a girl or a boy. That's it. For the second child, what are our options? Again, girl and boy. Those are our options, G, B. So we could have either had a girl first and then another girl, or a girl first and then a boy. Same thing down here. Our options are a girl and a boy. And then for our third child, a girl and a boy, a girl and a boy. So you're essentially just filling out this tree, making sure you get all the options. So that means that we have all of our options here. If we look, we can have girl, 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 or we can have girl, girl, boy. So right now, pause the video and see if you can write out all your outcomes. I'm going to come back with all of them written out. Okay, so these should be all of your outcomes that you have. There should be 8 of them. 4 of them start with girl, 4 of them start with boy. And then remember that the order does matter here, because you're talking about your first child, then your second child, then your third child. So your oldest, your youngest, or your oldest, your middle, and your youngest. So it does matter what order they're in. So this is number 7. Number 7 was draw the tree diagram. Let's look at number 8. It says write the probabilities for each stage's outcome in the tree diagram you developed below. Determine the probabilities for each of the 8 possible birth outcomes. So we know it tells us probability of a boy is 0.5, probability of a girl is 0.5. So that means out of 3 children, 1, 2, 3, I'm going to be doing 0.5 times 0.5 times 0.5 every time, because these probabilities are the same. So if I do 0.5 times 0.5 times 0.5, I get 0.125. So 0.5 times 0.5 times 0.5 is 0.125, and that is my probability for every single outcome, because all of them are the same. All of them are 0.5 times 0.5 times 0.5, because there's an equal probability of each one. So that means all of them are going to be 0.125. Question 9 says, what is the probability of a family having 3 girls in this situation? So if we look at our 3 girls, that's our probability of girl, 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 which is our first one. So if we look at that, our probability, we know for each one, is 0.125. Is that greater than or less than the probability of having exactly 2 girls? So let's look at all of our ones with 2 girls. Exactly 2. So that's not this one, because this one has 3. So here we have 2 girls, here we have 2 girls, 2 girls, and then I think that's it, right? 2, 2. That's our only ones with 2 girls, right? So that's 3 of them. So that would mean the probability of girl, girl, boy, plus the probability of girl, boy, girl, plus the probability of boy, girl, girl, which we know it's 0.125 each time. So you could do 0.125 plus 0.125 plus 0.125, or 0.125 times 3, which you get to be 0.375. So which one is greater, 0.125 or 0.375? Clearly this is greater. Also, we knew that there was 1 of these and 3 of these, and they're all the same, so clearly 3 is going to be bigger than 1. And again, we were adding and not multiplying, because this is saying like a what if situation. It's not one after the other, first child, second child, third child, Monday, Tuesday, Wednesday. This is a what if, so we're not doing one right after the other, so we're adding, not multiplying. And then this is our last question. What is the probability of a family of 3 children having at least one girl? Again, this at least should make me think that I am doing my 1 minus probability of no girls. What is the probability of having no girls? If we have no girls, that means we have all boys, B, B, B. And we know each probability in this one is 0.125. So 1 minus 0.125 is equal to 0.875, or 87.5%. Again, if this is confusing for you and it doesn't automatically make you think this, you can say at least one girl. Let me look at all of my ones with at least one girl. Let me see. We have at least one girl here, 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 here a girl, and here a girl. So all of these have at least one girl, so you could also add them all up. But it is easier to do 1 minus the probability of no girls. So that's the way we did it. That is the end of this lesson. If you have any questions, just comment on this video. But yeah, thank you. Have a great Monday.